Hi everyone, Samar here and welcome back to GoDevOps. In this episode, we will start interacting with the container itself and explore its life cycle. So let's dive in and start this episode.
So in this episode, we will be using the same Podman run command we have used in the first episode. So Podman run, the option 80, and the same image httpd. Now let's start the investigation. So the first command we'll use is Podman ps. And this command shows the containers that are currently running on the machine. So we can clearly see here the command ID, the image being used, the status, and exposed ports. Now something important to understand is that this command, so the command of Podman ps, only shows active containers. So if a container stops, it disappears from this list. And we already know that containers still exist even after stopping, so they are not automatically deleted. And that's where the next command becomes useful. So Podman ps with the A option. And the A option means show all containers, including stopped one here. So operationally, Podman ps will show only running containers, and Podman ps with the A option will show all containers. And honestly, this distinction becomes very important very quickly when troubleshooting or debugging environments. Now let's interact with the container itself directly. So let's stop it. So Podman stop, and we can put either the container name or the container ID. So here we have stopped the container. We can verify that. And now watch what happens if we refresh the browser. So the website is now unreachable because the containerized web server process has stopped. And this is actually a very important visual moment. So our service actually existed only because the container process was running. So when the container process has stopped, our service no longer exists. Now let's bring it back online with a Podman start command. And if we refresh again, so the service immediately comes back online, and this is exactly how container lifecycle management works operationally. So containers can be stopped and restarted very quickly without reinstalling application or reconfiguring the environment manually. Now, eventually, we may no longer need the container at all, and in that case, we can remove it completely. So with the Podman LM, and we put the container name. So here we removed the container. And now something very important to understand here is that removing the container does not remove the image itself. So here in Podman images, we still have our HTTPD image still available locally on the machine. So later, Podman can create a brand new container again from the same image without downloading it another time. And this distinguish between image and container is one of the most fundamental concepts in container workflows.
So operationally, a container typically moves through several states: created, running, stopped, removed, and understanding these lifecycle transitions is essential because almost all operational container management revolves around them. Because in real environment, things eventually fail, so services can stop responding, ports break, networking fails, or logs reveal unexpected behavior. And that's exactly why inspection and debugging tools are extremely important when working with containers.
So first, let's look at the container logs, Podman logs, with the L option. That means look at the latest container. And what we're seeing now is the output generated directly by the application running inside the container. Now let's generate some activity. So I'll refresh the website a few times. And now if we check the logs again with Podman logs for the latest. So here we can actually see the incoming HTTP requests appearing inside the logs. And honestly, this is one of the most satisfying moments when learning containers because you immediately see the relationship between the browser, the application, and the container logs themselves.
In most containerized applications, logs are written directly to standard output and standard error, and operationally this is extremely important because containers are designed to expose logs directly instead of hiding them inside random files everywhere on the system, and that makes debugging, monitoring, and troubleshooting much easier and more centralized.
Now let's investigate the container even further. Because a container contains a lot of metadata internally, like the state, the image details, the port mappings, and much more. So let's ask Podman directly with Podman inspect. So here, if we run this command directly, we get a huge JSON document, and honestly, beginners often get overwhelmed immediately here. So instead of reading everything, let's investigate specific useful informations with Podman inspect and less. So now we can navigate the output much more comfortably, and this becomes much more interesting when we ask real operational questions like which image was used, or which ports are exposed, or we can search for the container status. Or what IP address was assigned. And because this is how inspection tools are actually used in real environment, so not by reading everything, but by investigating specific problems. And this command becomes extremely valuable later when debugging for networking or deployment issues. So now let's move on to another command, Podman top. So this command shows the processes running inside the container itself. And now let's compare that with the host machine directly with ps grep httpd. And this is a very important moment operationally because the container processes is clearly visible directly from the host machine. So containers are not virtual machines. The processes running inside containers are still Linux processes running on the same host kernel. So the container simply provides isolation, controlled environment, networking separation, file system separation, and process organization, but underneath they are still regular host processes managed by the Linux kernel. And honestly, seeing this directly on the host system makes the container model much more concrete than theory alone. And this is one of the key operational ideas behind containers. So they are lightweight because they reuse the host kernel instead of emulating an entire operating system like virtual machines do. Let's do something extremely important. Let's intentionally break things, because in real operational environments, understanding failures is often more valuable than understanding successful executions. And honestly, this is where container behavior starts becoming much clearer. So let's start with a very common situation beginners encounter all the time. Let's take an Alpine image as an example. So Podman run docker u library Alpine. So now notice something interesting here. The container stopped immediately. And this is usually the moment where people ask, why did the container stop immediately? So at first, this behavior feels strange because many people expect containers to stay alive automatically, but containers do not work that way. A container only remains alive while its main process is running, and in this case, the Alpine image did not launch a long-running foreground process, so the process exited, which means the container exited too.
And this is one of the most important operational concepts in containers. So the lifecycle of a container is directly tied to the lifecycle of its main process.
Now compare that with our Apache container earlier. So Podman run the image docker u library http. So why did the Apache container stay alive here? Because the HTTPD process continued running in foreground mode inside the container. So operationally, no running process means no running container. And honestly, understanding this concept explains a huge amount of container behavior later on. Now let's move to another extremely common operational issue, which is port conflicts. Let's intentionally try using the same host port that we used for the Apache server container. So Podman run, we use the same port mapping. We change the image. Let's use the Nginx image. So here we immediately get an error because the host port 8080 is already being used by another container. And this is one of the most common networking problems in container environments. So two different processes cannot bind to the exact same host port at the same time. And now in real operational environments, the question becomes who is already using this port. And this is where Linux troubleshooting tools become extremely useful. So let's use ss with all these options, and this command shows listening ports and active services and which process are using them, and here we can clearly identify that port 8080 is already being occupied. So operationally, the problem is not Podman itself. The issue is simply that another process already claimed the port first. And honestly, this is real engineering work. So reproducing failures, understanding errors, investigating the system, and identifying root causes instead of randomly retrying commands. And that mindset becomes extremely important once you start managing real containerized environments.
And now that we understand how containers behave, how to inspect them, how to debug them, the next big question becomes, where do these containers actually come from? And we already know that behind every running container there's an image, and that's the topic for the next episode. So we'll finally explore how Podman manage images, registries, tagging, and the full image lifecycle behind the scenes. And of course, if you enjoyed this video and want to follow the rest of this series, don't forget to like the video and to subscribe to the channel, and see you in the next one. Thank you.